We're recording.
Thank you. All right, so we're going to begin by reviewing just briefly what did we do. We have an elastic bar in maybe I'll say, let's see. It's loaded in some way. Okay. We've got the strain energy potential. And from there, we went directly to the weak form through differentiation. And from there, we went to the strong form, which told us that, in fact, we're solving some very simple equations that most engineers see at in their very first introductory strength of materials course. And now we need to go to the Galerkin statement, which really is a discrete statement. And that's where we stopped. And then we talked about what we're calling the flex domain. So let's pick that up. So this is really something that's easier understood just through a sequence of pictures. So I'm just going to draw some pictures today, and hopefully we can all get on the same page. Okay, any questions up to now? Anybody like to ask before we dive into some new stuff? Okay, so what do we have? We've got our x-axis. Here's our x-axis. And then we've got, let's use blue. We've got a domain, let's say, that we're calling omega C. This is going to be what we call our CAD domain. It's the domain of the actual physical object that we're simulating. And then we've got another domain, which I'll do in red, that encapsulates this domain. So it covers omega C. Okay, we'll call this guy omega F. We usually use the term F for flexible. We're going to use splines to be able to generate domains in a very flexible manner. And we require that omega C. Oh man, did I just hit the wrong? It's one of the challenges of, gosh. Sorry, guys. You guys forgive me, my blunder. Okay.
I just keep thinking to myself every time I make a mistake on Zoom. With all the Zoom meetings, you'd think you'd get a hang of it by now, but all of us make these kind of mistakes, huh?
I always hit clear rather than erase every time.
Yeah.
Okay. Okay, fine. I'm going to make a. Okay, then we require that omega C be contained in omega F. This is the x-axis. So now we have to discretize, right? We have to somehow get a set of functions on these domains that we can use to approximate the solution to our PDE. So what we're going to do is we're going to create, we call this these portions of the x-axis where our problem is posed. We use the term physical domain. And we're going to discretize or create a set of basis functions in the parametric domain, which is related to the physical domain through a mapping. So let's go ahead and create another coordinate axis. Let's just call this xc. Okay, that's a coordinate in our parametric domain. Okay, and xc is our parameter. And what we're going to do is we're going to create the parametric representation of our flex domain. And we're going to call this guy hat, omega hat f. So when you see a little hat, that means parametric. And so we have this parametric domain, and it's somehow related to the physical domain. We can make the relationship concrete by saying that there is a mapping that we're going to call big XF that takes our parametric flex domain into our physical flex domain. Okay, and what we're going to say about this mapping is that it has to be bijective, which means that it's invertible. So there exists an inverse as well, right? So we're also going to realize that we need this inverse in a moment. So this exists. So we have this mapping, so we can take a point X and find a point XC, or we can take a point XC and find a corresponding point X inside the parametric domain. Okay. Now, let's leave this. So let's put a little more vocabulary here. This mapping here, if you notice, it's really, let me write this down here. That mapping is really a change of coordinates. Mathematically, that's all that it is. It takes on a couple of different names in finite elements. Sometimes we call it the geometric map. Okay, because in some sense, this map is what's defining our geometry. So you'll start with some parametric domain, and then you'll generate geometry from the parametric domain by defining this map XF. So it's sometimes called the geometric map. It's also could be considered to be actually from like a mathematical point of view, it's also called a parametrization. So if you ever hear that term thrown around, parametrization, it's an actual, it is a well-defined parametrization, meaning that we've assigned to omega f a set of parameters xc, and we can now write x of xc as our function for our geometry. Okay. All right. Now, let's remember that our problem is actually in omega c. So omega f really is not necessarily where our problem is posed. We're going to glue these two together, but it's important to remember that omega c is some CAD object. In general, that's how engineers create geometry for the most part, is they'll encapsulate it in some kind of a computer-aided design, and then they'll run a finite element problem over the top of that. Now, you might ask yourself, well, is there some parametrization or geometric map for omega c? That's a very reasonable question.
So in the traditional FEA sense, do they typically map omega hat f directly to c? And in this case, we're trying to make it more flexible?
Yeah,
Or do they
in
always do it this
general,
way?
yeah, so in general, you have a couple of options. The only requirement is that this relationship holds. So you can also do that omega c equals omega f, or you can do that omega c, let's say, is a very close approximation, or that maybe I should do, let me change the subscripts. I hate it when, one thing bad about Zoom is it has all these windows that are all over the place and they pop up and get in your way, and then they're hard to move. So obnoxious. I think they would have a way of, anybody know how to like get rid of the windows or, anyway. Okay, so the erase, so let me erase these. So let's look at two cases. There's several cases, but let's look at these two cases. So this is like an exact match. And then let's say this is a close approximation. Where do standard finite element methods fall?
Hopefully close approximation.
Usually it's here. It's a close approximation. There's things done to omega c either to simplify it or to change it slightly, so you can create this mapping xf. So we call this type of a method is called, generally speaking, an isoparametric finite element. Okay, where it's just an approximation. It's a close approximation. What would we call a method where, in fact, they're exactly the same? In other words, we can generate this geometric map, x sub f, that maps exactly onto omega c.
Was that isogeometric?
Yeah, that's what we call an isogeometric method.
So in that case, would your xf be the same as your xc as well?
Yeah, that's a nuance that I didn't put up here, but it's important. In fact, isogeometric, what we've said here is just that the actual representation of the geometry is equivalent. That's pretty strong, but even stronger is to say that not only are they equivalent, but that they actually have the exact same change of coordinates function that defines them. So we could write that like omega, well, let's just do it this way. But it's good to distinguish between the two because they're not the same thing, right? So you could say that x sub f is equal to x sub c. So between this guy and this guy, what's a stronger statement between those two? Which is a stronger notion of equality? This is a pretty important point. What's the difference between these two statements? Maybe that's a better question.
Well, one is a mapping to that, and the other one is itself. So I guess if the mapping is exactly the same, that would be a finer representation, because even though the geometries match, you could maybe have the maps be slightly different because they're a subset of the other.
Yeah. So if these maps are identical, then that, of course, implies that the geometry, right, the result of the mapping, the range of the mapping must be equal. But do you see how omega f being equal to omega c does not necessarily imply x sub f is equal to x sub c? In fact, this isn't unique. Right? Like, how many different ways can you represent a line, right? I mean, you can do it an infinite number of ways. So in fact, this statement is not as strong of a statement as this statement here. Usually when we use the term isogeometric, even though most people aren't thinking through these subtleties, they mean the former. They mean this very strong statement. But in fact, you could make an argument that this also is isogeometric because the same geometry is being used, even though the parametrizations may not match. Okay. So the function used to create the geometries may not be the same. Okay, let me stop and answer questions about that. I really want to try and help you understand this point because it is a big one.
Is there an example where omega f equals omega c, and how those might be equal, but then the mapping would be different? Could you give an example of that?
Yeah, sure. So let's look at the line. Okay, here's a line. Let's say we map. Okay, so let's say we create some basis functions. And then we create our map. These are the NAs. Let's say we create our map X F equal to let's see. Actually, we could probably do this.
I was just thinking, wouldn't it be the same? Wouldn't it be kind of with XF and XC? Wouldn't it be more like you discretize one in like maybe smaller sections on the left and larger sections on the right, and the other one you did smaller sections on the right and larger sections on the left, and it's your discretization that is actually different? Isn't that more equivalent to XF and XC than doing like the basis?
Here we go. Here, I'll just give in. I didn't quite follow. Let me come back to that, Eric. That was a lot of information that I didn't quite capture because I'm trying to think through the first question. Okay, so XC and X, here's a mapping. Why don't we just make it linear so that X equals XC, right? So if this was 0 to 1, then this would be 0 to 1. Do you see that? You see this mapping? It takes every XC value and just maps it in a linear fashion to the corresponding X value. Everybody okay with that? Okay, now why don't we make our geometry X sub C equal to XC squared? Okay, so the endpoints still map. So 0 squared is 0, so it maps there. 1 squared is 1, so it maps there. But the internal points don't map the same way. See how these parametrizations are different? Even though you notice that omega, in this case, omega F is equal to omega C, right? Do you see how this 0 to 1 segment is being mapped in both cases to the X coordinate, 0 to 1? Everybody okay with that? Lindsay, do you see that?
Yeah.
But notice that the parametrizations are different, right? Because if I take a point, let's say 1/2, so if I plug 1/2 into this function, what does it give me? 1/2, right? But what if I plug 1/2 into XC squared? It gives me 1/4. So in this mapping, the points are being bunched up, right, to the left. So it's the same geometry, but a different parametrization.
Mike, in this example, omega f equals omega c, are you saying that the domain are the two discrete points 0 and 1?
The domain are all the points between 0 and 1. Yep. So let me...
Oh, okay, I see. Okay.
So like all the points exist in both of those spaces from 0 to 1, but there's more, like if you were to look at them discretely, there's more data points on the left in the squared term than there is in the other.
That's right. That's why parametrization is important. So omega C our CAD geometry are all the points between 0 and 1.
Okay, I see. Thank you.
And omega f in both cases is also 0 to 1. But these parametrizations, if you look at dxf, dxc versus dxc, dxc, do you notice that this one is just 1, and then this one is 2xc? So anyway. So this is a huge point in higher order smooth finite element methods that I don't know, I don't think I can emphasize it enough. At this point, it may seem like a subtlety, but it's actually a massively important concept, is that just because you can match geometry doesn't mean you have a good parametrization for that geometry. And as we move forward here in a moment, you'll see that the way that we get our basis functions for discretization, we use the parametric domain coupled with the parametrization. And so the parametrization has a big impact. Okay, so an isogeometric, back to the original point, which is an isogeometric method. I don't think the community has made a clear distinction between whether the geometry matches in physical coordinates or the underlying parametrization. If you look at the literature on the method, implicitly in almost everything, they're assuming that an isogeometric method has to have the same parametrization. In fact, that's not the way that I interpret isogeometric methods. I would call this maybe it would be like an isogeometric method, and then we need to come up with some other descriptor when the parametrization is exact, because this word means same geometry, not same parametrization. Yeah, maybe we could use a play on isoparametric. Anyway, all these words, like even when you look at them closely, they kind of, yeah, kind of look at them with squinty eyes a little bit, because they're a little. It's funny how these communities, they're not even self-consistent sometimes. Okay, what do you think is better, by the way, between these two parametrizations? I mean, couldn't we make this like xc to the 100th? If you had xc versus xc to the 100th as your, which parameterization do you think would be better?
I mean, back when you had the xc squared, it kind of would depend, because if you had something where you have a lot of stuff happening on the left side near 0 and not much happening over there on the 1, then potentially you want to move all of your data points to the left so you can have better fidelity over there. But most of the time, you probably want it more evenly dispersed.
Yeah, Eric, that's exactly the right intuition. This is this is called a linear parametrization. And all classical low order finite elements enjoy this kind of behavior for the most part, this linear behavior. And it is very conservative. It kind of equally distributes all the points through the parametrization. But you can see that the fact that you can control parametrization is actually a tool too that you can use to your advantage. Like this one would scrunch all the points up here, and then they become more spaced out as you move to the right. Okay, and so
so they call the other one like biased parameterization, or would they, or is it just there's a whole bunch of other types of parameterization? It doesn't have to be biased.
Honestly, Eric, what I'm presenting here, there has not been anything introduced into the literature that gives this fine detail on. We're gonna have to, maybe you can suggest a name. Because the reality is that the isogeometric community really is stuck here. And that's kind of a dead end a little bit, because it's so stringent. yeah, so anyway, the answer to this is there is no answer yet. In other words, there is nothing that's been like accepted in the scientific community as the right way to describe these things. Okay, so let's back up now and go back to what we were talking about. And let's combine the parametrization with our basis functions that we're going to define now. And there you'll see how everything kind of comes together. I just want to erase just this part because I don't want to redraw everything.
They need to give you a bigger eraser.
I know. Let's see if I hold this down, maybe. No, just one eraser. I only get one size. Oh, well. Yeah, so parametrization, that's like something you can sit and think about for a while. Like I think there's a lot there. It's a very important concept. So we have this XC, and we have some domain, but the reality is that this is usually kind of fuzzy. We don't necessarily have this, right? Like, in fact, a lot of the common CAD formats that are used in mechanical design, they're put together in such a way that they create a geometry, but they break the parametrization. So the parametrization may in fact not even be well defined. And so this is one of the reasons that we create just a close approximation, is because we often don't have this. We don't have access to the original CAD parametrization, or the CAD parametrization is so poorly defined that it's not suitable for simulation, okay? This is one of the reasons we have this idea of a flex domain that just encapsulates the CAD, because then any kind of CAD description, we should be able to come up with a method that can handle it, regardless of how poorly parameterized it is. Okay, so now what do? All right, so we need to discretize, which means we need to introduce a set of basis functions. And so we're going to go ahead and introduce our basis functions. We always introduce them in the parametric domain. That's standard, because we have in some sense, we have control over the parametric domain. So let me draw some basis functions. So we have omega hat f. So what do? Well, the first thing we do to create our basis functions is we create some elements. So we take omega hat f and we subdivide the parametric domain up into a set of subdomains. And we call these elements, and we'll use the notation omega hat f sub e is an element, okay? That's called an element. Okay, so we create a whole bunch of elements. Then we have to begin to create a piecewise polynomial definition, right? We're not gonna have like one domain or one element in really high degree. We wanna leverage splines. And so let's go ahead and define a spline. And maybe I'll loosely define it here. A spline, generally speaking, it's a piecewise polynomial where the adjacent polynomial segments are smoothly combined. In general, that's what a spline is.
That's not how they typically do it in the traditional FEA, right?
So in traditional FEA, if you interpret like a C0 smoothness as smooth, then yes, all low order FEA are also splines. But in general, splines almost always denote a higher level of smoothness than C0. So you can use the term correctly in the context of traditional FEA because they are piecewise polynomials that are where you have a bunch of polynomial segments that are connected across element boundaries, but that connection is just C0.
Right.
So that is a spline.
It just doesn't look smooth. It looks jagged.
Yes, but normally if you look at what a spline, like a mechanical spline, was used for, it was to accomplish a smooth fitting. That was their purpose. And so usually when people are talking just in casual discussion in this field and they use the term spline, they're kind of implicitly implying some level of smoothness, although mathematically that needs to be defined. Okay, so what do? Well, we have to create polynomial segments over each element. So what we do is we say, well, what degree polynomial do we want? So we assign a polynomial degree to each element, right? So we'll denote that by P sub E, right? So now we're starting to get that an element is defined by a domain and then a polynomial degree. What we're assigning to every single element. And then the last part that comes from the spline, we need to define what level of smoothness we want across boundaries. And we're going to use the notation K to denote smoothness. So if K is equal to 0, that's C0, C1, and so on. So the K comes from the standard notation C to the K, smoothness. So we're going to define, like if this is element 1, we'll have polynomial degree on element 1, a polynomial degree on element 2. And they can be different, a polynomial degree on element 3, and so on. And then here we're going to have some K1, K2, K3, K4, K5, K6, where K1 and K6 are assumed to be -1. It's the end of the intervals. Let's just make it discontinuous there. Okay, so that's getting a little messy. Maybe I'll draw it again down here a little bigger. We have our parametric domain. Let's just make like 4 elements. Okay, an arbitrary element. And we'll make E, F hat. We've got P1, P2, P3, P4, K1, K2, K3, K4, K5. Okay, now what we're going to do is we're going to define a polynomial basis for each element. And you can pick any polynomial basis that you'd like. We're going to tend to favor the Bernstein basis because it kind of has a close connection to splines for several reasons that we'll talk about as we go. So let's say we pick quadratic polynomials for every single element. So then what we're going to do is we're going to come on every element and we're going to build a quadratic Bernstein basis over every element, because then we know that over this element, using this basis, I can represent every quadratic polynomial. I do the same here. All quadratic. Okay, so now I have 4 Bernstein bases. At this point, they're discontinuous across element boundaries. I haven't done anything with the smoothness. So let me label them: B1, B2, B3, B4, B5, B6, B7, B8, and B9, B10, B11, B12. Okay, so these 12 Bernstein basis functions, they span a space of polynomials. Do you see that you could represent a polynomial segment over this element? You could represent a polynomial segment over this element, and so on, right? You could have 4 polynomial segments. They'd be represented in terms of these 4 basis systems of basis functions. But we're lacking any idea of the smoothness. Everybody okay with that? Let me pause to take any questions. Is there any questions on this? Okay. So tell me about the space. So if I was to put all of these Bernstein polynomials in a little set, let's say, can you tell me something about the span of these 12 functions? What CK space is it in?
CK0?
So is K equal to 0 yet? Have we enforced any kind of continuity at all? So it's not
I guess K is undefined then?
It's -1.
Oh, at this point it's -1 because they're discontinuous. There's discontinuity.
Yep. So this guy, the span of these Bernstein polynomials is contained in the set of all discontinuous functions. Everybody okay with that? Okay. So what I want is to enforce some smoothness here. So let's figure out how that could be done. So if I want C0 smoothness, like if all the K's were 0, how would I enforce that?
You'd have to set like B3 equal to B4 at B4 is at 0 and B3 is at, well, I guess it would be -1 to 1, right? Is that what we're doing with Bernstein? So B3 equals B4 at their intersection point, but it'd be different for B4 than it would be for B3.
Let's call this like 0, 1, 2, 3, 4. Right, so we want B3 to be equal to B4 at 1. We want B6 to be equal to B7 at 2, and B9 to be equal to B10 at 3. You see, if we do that, we just close this little gap, right? And B3 and B4 become the same function. So this becomes one function. So we take 2 functions and combine them into 1 function, okay? For these 3 guys over these 3 element boundaries. All right, now this is just a little equation, right?
Mike, I had a question. So when you're setting B3 equal to B4, are you, I mean, I know pictorially I can see that, you know, they are the closest to each other, but are you choosing B3 and B4 because their value is 1 versus like B1 and B2 are equal to 0 and B5 and B6 are equal to 0 at x equals 1?
Yeah, Lindsay, that's a great point. This is one of the reasons I'm using the Bernstein polynomials, because notice this nice separation, right? For C0 continuity, notice every function is 0 except 1 on each element, right? So C0 continuity can be easily achieved by simply setting these 2 equal to each other. If you had some other functions that were non-zero, right, then you'd have to include them in a more complicated relationship to achieve continuity, right? So the fact that there's just these two functions coming to +1, every other function is 0, makes the algebraic system, these equations, it makes them very simple. And in fact, if I want C1, it's the same thing. If I want C1, it'll involve, like if I want C1 at 1, it'll involve B3 and B4, and then B2 and B5. And if I want C2, it keeps moving out radially. Do you see that? That is a unique property of the Bernstein basis. And it's one of the reasons it's nice to talk about building continuity in terms of the Bernstein basis, is because of this property. Okay, in general, what we're gonna do.
Well, isn't B1 always 0 at 1, and B6 always 0 at 1?
Yeah, but their derivative isn't. You see, if you want C0, you just take the values of B3 and B4 at 1 and make them equal to each other. If you want C1, then you have to take all of the functions whose derivatives are non-zero, which is B3, B4, B2, and B5. In fact, the first derivative of B1 at 1 is identically 0, so it's not involved.
Mm-hmm.
So that's how you do C1. And then C2, you need to take all the functions whose second derivatives are non-zero at 1, and so on. So the Bernstein has this nice separation of derivatives, where if you want C0, it involves B3 and B4. If you want C1, it's everything that was involved in C0, and then the next row of functions, B2 and B5, and so on.
But is it their derivatives at C1, or is it both?
C1 is derivative information. Yep.
Yeah.
C1 is you want the first derivatives to match. So you have to take all the basis functions whose first derivatives are non-zero at 1 and come up with a relationship between them. So that
You're saying that B3 and B4, if you're in C1, B3, the derivative of B3 and the derivative of B4 should be the same?
What I'm saying is there is a linear relationship between B2 and B3. You have to combine them such that the slope of the resulting polynomial segment matches the slope of the polynomial segment created by B4 and B5. That's what C1 continuity means.
Yeah, so B3 and B4, because they almost look, they're like,
B3
they almost
and
look
B4,
like they're never going to be the same, but because you're adding B2 to B3.
Yeah, so what you do, B3 and B4, those degrees of freedom are used to enforce C0 continuity, and then you take the result of the C0 combination and manipulate a few more degrees of freedom to actually make not only is it C0, but then the slope has to be continuous.
Yeah, okay, that makes sense.
Okay, so the way that this is done, let's just back up rather than getting into all these details. One of the things that we can write, what we can say, is that what we want to do is we want to find a linear combination of our Bernstein basis functions where they're recombined in order to satisfy the smoothness constraints that generates a new basis that has that smoothness. So let's say we want to take this so we have 4 elements, okay? So there's 1. Okay, and let's say we want K to be equal to 1 and PE is equal to quadratics. Okay, so we have a C1 quadratic spline space, and in fact I know what this looks like ahead of time. It looks like this. Let's call these N1, N2, N3, N4, N5, and N6. Okay, so this is C1. This is a C1 spline space. So the span of N, okay, A equal 1 to 6 is going to be a subset of what? If this is a subset of C minus 1 and K is equal to 1 everywhere here, what should this be a subset of? You okay with that? C1 functions, right?
Are the endpoints also k equals 1?
Well, we kind of ignore the endpoints, okay? Because
okay.
there's nothing, the domain ends, right? There's nothing out here. It's just, okay.
Then I agree.
All right. Now, what's the relationship between C1 and C to the minus 1?
The translation between the basis and the actual.
So every C1 function lives in the C minus 1 space, right? A C1 function is also a C minus 1 function, okay? So all C1, this space is a subset of this space, right? So what does that mean in terms of the relationship between these basis functions on the right and these basis functions on the left?
The ones on the left are contained.
Yep.
And just to double check, is C negative 1, is that integral, essentially?
No, this is the discontinuous functions.
Okay.
Okay, this here, because C1 is contained in C minus 1, then the span here, the span of these guys, since everything is polynomial, is actually contained in the span of these guys, which means there's a linear transformation between your discontinuous Bernstein polynomial basis and the smooth basis that you're interested in. Okay? We call this operator C, it's a matrix that this matrix, the rows of the matrix take linear combinations of the Bernstein polynomials to generate your smooth functions over here. This is called an extraction operator. Okay, and this is how we build our splines. This is the fundamental idea.
So why do you need to have this extraction operator to get from this discontinuous function space to this continuous function space if you haven't defined either one of them yet? Why can't you just define your continuous function space as your space for sigma hat FE?
Because we don't know what these are usually. In the very simple case, this in fact is nothing more than a B-spline. And B-splines are also, these are piecewise polynomials. So they're in the background is this always, whether you see it in the literature or the books that you're reading, at some point people stopped, B-splines became so ubiquitous that people stopped talking about how they were created and they just wrote down algorithms, right, for creating B-splines. But that came after they figured out how to generate them as linear combinations of these, of polynomial segments that are discontinuous, right? This is the generic, general way of understanding a spline.
So those Bernstein basis functions that are C-1, these ones we do know how to map those directly to our sigma hat F.
This domain here is omega hat F. We're defining both of these spline bases are on the same domain omega hat F. Okay, and so what I'm saying, I mean, if you think about what we've done in the course so far, we know how to build polynomials over a domain. And we know in some sense that we can enforce a certain level of smoothness. And so since we know the relationship between the spaces, we know there must exist a linear operator that takes us, it's like this is actually, guys, a change of basis matrix. That's all this is. You have to be able to do a change of basis if two spaces are nested. And so regardless of how you define your spline space in terms of your elements, degrees, and smoothnesses, the question then becomes, how do we algorithmically construct C? We're going to come back to that. For now, we're going to assume that C is given. Okay, somebody will give you C, and it will help you take your polynomial basis and reconstruct your spline basis. And then this spline basis is what ends up being your basis of your parametric flex domain, which is where we'll pick up next time. Okay, so let's stop there. I'll stop lecturing, but I'll hang around for a few minutes if you want to keep talking about this.
So Dr. Scott, a quick question for you real fast. I think I might have missed something. I don't understand how we went from a C-1 in the, I guess in the case where you're using the Bernstein basis, to a C1 when we switch over to our spline. Because I thought we were enforcing like a K0 constraint. And so in that case, I thought it'd be C0, and I don't see how we get to C1.
What I'm saying is this is just a specific example.
Okay.
Pick anything you want. I just picked a specific example. Mathematically, all that matters is that this smooth space that you create, if it is contained in this space, then you know there's a linear transformation. It exists. Whether you can compute it, that's another question. But mathematically, we know it exists. And so what I'm saying right now in the class, that's sufficient. We're just going to assume this exists, and we'll come back to the algorithms that compute them later. But for right now, we know it exists.
So given the constraint that we want to place on our basis functions, though, does that determine what space, I guess, our spline should be contained in?
Yes, exactly. So as soon as I write down the degrees and the smoothnesses, it defines a spline space. Okay?
Okay.
And then I have to compute a basis for that spline space. That's the hard part, right? This basis here, N1 through N6, it is not unique, right? There's an infinite number of possible bases for the C1 quadratic splines. What I'm saying is that there exists a linear transformation, in fact, many of them, that can give us that relationship. They can generate a basis.
Okay.
So everything we've done up to now is very, very important. Like all the information that I presented in the previous lecture notes, you need to understand because it's all starting to come together, right? We've got discrete spaces, splines, linear transformations, you know, spans, subspaces, all that stuff is coming together. But the punchline is that if I can write down a parametric domain, define the polynomial segments and the smoothnesses, I know there exists this linear transformation, and I'm going to leverage this in finite elements to generate very, very general spline spaces that we can use for all kinds of things.
Mike, is
Okay.
the fact that C being, since that's non-unique, does that create a problem when you go about finding it later down the road?
What I should say is that we can put a few more constraints on the nature of the resulting basis that we want that can make it unique. So if we start defining things like we want the basis to be positive, we want it to be like sparse and all that kind of stuff, then there is a uniqueness that pops out. But that's
Okay.
much more advanced idea. For right now, all I want you to understand is that, well, actually, I'll continue this next time, and I'll show how we use this from a practical point of view, and then it should become much clearer.
And then, Mike, I had another question. When we were talking, and I just might have missed it, when you were talking about the isogeometric versus isoparametric statements, would you argue that one is more preferable to the other? I understand that the isoparametric is a stronger statement, but I was wondering if that was helpful or more of a hindrance.
Okay, so boy, there's a lot of nuance to the answer to that question. So an isoparametric method means that the geometry is defined through the same parametrization that you define your solution fields.
I think isn't she asking that? Lindsay, are you asking when you say isoparametric, are you saying xf equals xc?
Yes, I was using the the definitions that Mike had kind of made.
Yeah, so isoparametric in the normal finite element literature, they never assume this, ever. Because they can't do this. They don't know how to do this. Isoparametric means that they throw away the CAD and they generate a new geometry that comes from the parametrization that they pick, right? That's what you do. You put a mesh, you overlay it, and then that becomes your geometry. So isoparametric never means in the traditional literature of finite elements that somehow somebody has defined a CAD object and then you've figured out how to generate the exact representation of that parametrization for simulation. The reason that never happens is because the CAD parametrization usually is complete garbage. So you couldn't even use it for computation even if you wanted to. So isoparametric finite elements always assumes you throw away the original CAD parametrization and replace it with x sub f, where now x sub f is basically an approximation to x sub c. So what
don't you mean that it's omega f is an approximation to omega c?
Well, this is the same statement here. It means the same thing. So what's preferred? Well, the absolute preferred thing is that there's a CAD system out there somewhere that you can generate anything you want on a computer, and then that underlying parametrization is suitable for simulation directly. That's the holy grail, right? That's the strongest notion of isogeometric. It's also isoparametric by definition. But since CAD is not suitable for simulation, you have to come up with an alternative. And the next best alternative probably would be something like what we're presenting here, where you separate those two parametrizations and then come up with a way to generate the optimal flex domain for the simulation at hand, which is what we're presenting here. Did I come anywhere close to answering your question?
I'm gonna have to think about that for a little bit and digest it, I think. But you're saying, in summary, in application. Okay, yeah, maybe I'm not understanding the summary or the larger picture of what you're saying.
Yeah, there's a lot of information that I've given out today, right? And all of it requires some thoughtful consideration. So maybe let's pick this up on the next lecture to give you a few days to kind of digest it. If you look in the lecture notes towards the bottom, I have a whole section on this that you can review that maybe will help solidify some things.
Okay, that sounds good. Thanks.
Okay, do I have any other questions, or are we tired?
So-
Just
Yeah.
okay, I have a quick question. So since you're saying that these spline bases aren't unique, just says I don't know, as a way to understand, does that mean the two spaces that we're considering are not isomorphic?
What I'm saying is okay, so if your basis, so if you pick a basis for your smooth space and a basis for your non-smooth space, then there exists a unique linear transformation between them.
Okay.
Okay, but since there's multiple bases for any given space, there's going to be multiple transformations, right?
Okay.
It's not that you can pick like two vectors and come up with two different linear transformations that map the you know what I mean? It's still
Right.
yeah, it's still a unique in the sense if you give me a right hand side, a unique right hand side, the operation is unique.
Okay, sounds good. Thank you.
Okay, Chris and Kaylin, can you guys just hang on for a minute? And
Yep.
then let's stop here. Thanks everybody.
Sorry, did you say Kaylin or Caleb?